Hello and welcome to the lecture Field of View and K-Space, the Final Frontier. This is chapters both 15 and 16 from MRI, the Basics. And so that will get into things here. So the learning goals for this material are really centered around field of view, or FOV as we abbreviate it, and resolution. And we want to understand this both from a couple different perspectives, a frequency encoding perspective, and then more generally a K-space perspective, and then also bring aliasing, an understanding of aliasing into this material as well. So let's start off with this picture showing really the data flow in our experiment, right? And so we start off with what we often refer to as the data space, but really the key thing to note here is that the dimensions of this are the dimensions of our experiment, their time, for example. So it's shown on the horizontal axis, it's the sampling interval and the sampling time. So this is on the order of milliseconds. This is our frequency encoding. And on the vertical axis, this is our phase encoding, where we're incrementing TR to TR, filling up our data matrix. And then what we've now covered with the K-space perspective is actually when we have knowledge of the magnetic field gradients, we can go from this data space and our sort of experiment dimensions here into K-space, where now these K-space, for example, might be of units of, say, inverse space, so inverse centimeters, which will correspond over here in our image to units of centimeters. And so we take our time information, we take our magnetic field gradients, we convert things into K-space, and then the last step here, as we know, is a Fourier transform to create an image here. And we're going to, there's key quantities are shown here that we're going to use. First of all, these delta kx, ky, the delta xy, kx max, field of view x, field of view y, that we're going to go through in this lecture. So let's think about what information do we need to move through these different domains. Right here in this step here is where we need to use the information about our gradients. And as we've covered, it's our magnetic field gradients over time that define our K-space trajectory. Then the step here is simply a Fourier transform. And this moves us from the K-space to the image domain here. So the first way we're going to look at the field of view, or FOV, is through sort of a frequency encoding interpretation. So the same way we initially looked at the concept of frequency encoding, we're going to look at how we can put field of view into this interpretation. Okay, so let's start off with our simple frequency encoding pulse sequence here, where during the time the magnetic field gradient is on, we have this relationship that frequency is the gyromagnetic ratio times the readout gradient amplitude here times position. And then we're going to define a some data sampling interval now, as we covered in chapter 12. So we have this data sampling interval, delta TS, and with the Nyquist theorem says is that this sampling interval supports a bandwidth, or supports a sampling bandwidth, and I'm going to refer to this as RBW for receiver bandwidth. That is proportional to inverse of the sample spacing. Or if I draw this in the plot over here, I'm going to say in the frequency dimension, the region that we can define without aliasing is going to be this, some bandwidth, and now we're going to call this the RBW, the receive bandwidth. This is the region that we can define unambiguously with a given sampling rate. And look back if some of this concept does not make sense. Also, I encourage you to review chapter 12. And so now we're going to use this picture of mapping frequency to position to determine, well, actually, as with all of our magnetic field gradient manipulations, the frequency corresponds to a range in position. And in fact, this is what we're going to define as our field of view in this frequency encoding or X dimension. And you can derive from this relationship here that the field of view in the X direction will be the receiver bandwidth divided by gamma bar times the gradient readout gradient amplitude, or this is the same as rewriting it in terms of the sample spacing. This would be 1 over gyromagnetic ratio times the readout gradient times the sample spacing. Okay. So what we've done here is we figured out for frequency encoding what our field of view is going to be in that direction. It's going to depend on our gradient amplitude and then our sample spacing during the data acquisition. But now what we want to do is that works for frequency encoding, but when it becomes to phase encoding, things become a little bit more tricky. So we're actually going to use the case-based perspective to derive a general relationship for defining the field of view. And there's this exact same relationship that we had in frequency space. So sort of refreshing that on the top here, recall if we had some signal in time and we sampled it, and just like in the last slide, at some rate of delta TS, and in the Fourier domain, so our frequency domain, this corresponded to, again, having a bandwidth or a supported frequency range of 1 over this sample spacing. The exact same thing holds true when we're going between case space and image space. And remember, the common thing here is we have a Fourier transform between these domains. So in one domain, if our sample spacing is, for example, delta kx or delta ky, then in the Fourier domain, that's going to correspond to our region of support, or the maximum area that we can unambiguously recover, which we refer to as the field of view, is going to be the inverse of this sampling rate or sample spacing. And so that's what these two relationships here are going to say, is that we're going to just, this is what Nyquist tells us, is that the field of view is proportional to the inverse of the sample spacing in the case-based domain. Okay, so let's just go through some of the same illustration that we've gone here before. So now we've run our experiment, we've used our gradients to determine our location in K-space. we have some potentially continuous valued data in frequency encoding dimension. Maybe this corresponds to an object. What we're going to do is, due to our time sampling, that's going to lead to some digitization or sampling in k-space, the sample spacing delta kx. And what that does is that leads to repetitions of our object at 1 over delta kx, or also recall, if we look at things from the discrete sampling domain, this means that when we do a discrete transform, our signal, our Fourier transform is only defined over the region where there's it is repeated. So we would get back, as I've drawn it in this case, our original object, the range that we're going to be able to recover is going to be 1 over the kx sample spacing. And that's going to be defined as our field of view. And we should, I'd like to draw that in this stage, this is the, for example, the k-space data of our object that we're sampling. We're sampling this data in time, and then so we have some signal over time. It's going into analog to digital converter, and then we're putting that into our data matrix, or our k-space matrix. And this is for, I know this is, here I'm talking about frequency encoding. Now the picture in phase encoding here. So the distribution of our magnetization that leads to the k-space data is it'll have some pattern, just depending on the object, right? And we're going to sample that Fourier transform data. Some sample spacing, now this time delta ky, which would lead to, this is our picture of Aliasing the repetitions of that object at this interval delta ky, or if we look at this in the way we actually perform this, which is with the discrete Fourier transform, that we only get the, what we see is the unambiguously defined region here, again still 1 over the sample spacing, which is now going to be the field of view in the y direction. Now, just as a point of clarification, recall that, or that's going to become important in a second when we look at aliasing, is that in this case we don't have a continuous valued signal in time. We have a signal coming from each TR, Okay, so there's not this analog to digital converter step in phase encoding. We just fill this in, one, say, TR at a time. Okay, and I'll get back to this point in a minute. Okay, so what I'd like to do here is go back to now some of our gradient amplitudes and other parameters. The parameters that are going to be relevant first for defining the field of view. So we sort of know what these are going to be for frequency encoding because we already looked at this relationship. And if we highlight this period here of the readout, we're going to do some case-based trajectory like this. And I'm going to have some sampling rate, which is in time, which is going to lead to some sample spacing in case space. And a distance in case space is how I call it, case space is proportional to the gradient area during a time interval. So the amount of case space, so what we're really trying to look for, and we can look at it in this plot, is say at this sample and this sample here, the little height here, or the height distance here, this is delta kx, like how much have we moved in delta kx over this small time interval here. And turns out it's going to be proportional to whatever this gradient area is, because I just draw my quick case space equation. Case space over time is the integral, the cumulative integral of the gradient. So it's just going to be that gradient area. In this case, it's a nice rectangular gradient, so it makes it very easiest for us. So it's the height of that gradient multiplied by the time interval. And nicely, we're going to see that this matches up with our previous result. If it didn't, then I should be very worried. I'm doing something very wrong if it didn't. Okay, so if you look back at a few slides, it's exactly the same relationship we had before when we used just the frequency encoding interpretation, not the case-based interpretation. Now the power of the, okay, and so here I want to, now using this perspective, I want to revisit this concept of aliasing, the frequency encoding direction, and what can happen here. And the key thing is to remember that a frequency encoding signal, again, is a signal that's acquired in time. And so what we're actually going to do in practice is we are going to run this through this anti-aliasing filter, this low-pass filter that we defined in Chapter 12, prior to doing our analog to digital conversion. Which then gives us discretized data. Okay, so we still have some underlying distribution of our signal. Let's say we choose a sampling interval that is actually too far apart, so such that we would expect to have, or we're not going to support this whole range here. But recall what's going to happen, and let's give it a little color here, is that what our anti-aliasing filter is going to do. It's going to multiply this. It's effectively multiplying our Fourier transform data, or in this case our image data, by some filter or by some function here that has a width that we can define. Let's match it to the sampling rate. And so this is what this is kind of a refresher here from what we saw there, but this is actually going to limit, in fact, the extent, or it's going to limit the field of view of our reconstructed image. And so when we look at the continuous transform and we have these repetitions, or when you go to the discrete case, we're going to get an image in the frequency encoding direction that is aliasing free, regardless of whether our field of view is smaller than the size of our subject in this dimension. And this is because of the anti-aliasing filter. And we can apply an anti-aliasing filter here on continuous value data as we have in the frequency encoding dimension. Okay, so bottom line is here, we can use the anti-aliasing filter in frequency encoding to not get aliasing. Okay, so now let's shift gears to phase encoding and figuring out how we define the field of view using this case-based perspective for phase encoding. So let's draw a nice large size, kind of exaggerated phase encoding gradient, in which we'll send this out to some location in KY. And for example, we would acquire with that one line in case space. And then we have the next step of our experiment where we're going to change the phase encoding gradient amplitude. If we go into the case space perspective, we don't travel quite as far in case space, or we acquire this next line in KY. So then the trick from the Nyquist theorem to define what the phase encoding field of view is to figure out what is this spacing between our phase encoding lines in K-space. What is this delta KY? And turns out we can look at this also in terms of gradient areas. And so really the difference in KY here is the difference between the orange gradient area and the green gradient area, which is simply, it's relatively easy to annotate here, simply this yellow area. So whatever the times gamma bar. So to get to there, I'm going to have to put in a few values here. Here's the notation we've used for the gradient time. And now I'm going to introduce a notation here that I often use for the, actually not the, and you'll see the reason for this as we go through it, but the gradient at the phase encoding gradient increment, or GY I. And this is the amount that we're changing the phase encoding gradient between each TR. And this is exactly the thing we need to know to define the field of view. So now we can work out what this gradient area is. It's simply gamma bar times this increment, the difference in phase encoding gradient amplitude times the duration of the phase encoding gradient. And thus we're going to be able to determine our field of view and y and the relationship of that to our phase encoding gradient increment. Okay, so here we can go now all the way from pulse sequence to k-space to defining the field of view, or you can often, is what's going to be the problem in the experiment, is doing the reverse, having a desired field of view that you want to achieve, designing the gradients accordingly. Now, let's revisit aliasing discussion and phase encoding. Now, phase encoding is inherently different from frequency encoding in that it's truly discrete sampling, and which means we cannot do an anti-aliasing filter. Just to refresh, here's this picture of, we're going to acquire one, line of k-space here at a time. And so there's no anti-aliasing filters require a continuous valued signal to function. And we just simply do not have that. So what can happen in phase encoding? So we can look at the distribution of the spatial frequencies of our net magnetization of ky. Give it something different here. It looks something like this. And if we do make the mistake of choosing our delta ky sampling to be too broad, let's illustrate what's going to happen there. Is it will have our original object here, but we certainly could have some overlap. And again, we can't do, in this case, these are just inherently discrete samples, so we can't insert an anti-aliasing filter in here. So what we're going to get in our image is going to be this aliased image. If I can draw it, I'm gonna something like that. Here's our field of view. And I sort of have, these little bits of aliasing folding over. And so the bottom line here is that in the phase encoding direction, we absolutely can have aliasing. So we need to be much more careful, with our sampling in the phase encoding direction. So the summary here, again, frequency encoding, our field of view is primarily determined by the receiver bandwidth, but also the readout gradient amplitude, and we can apply an anti-aliasing filter, so we never have aliasing in frequency encoding. Phase encoding, the field of view is determined by the phase encoding increment, so how much we're changing that gradient from TR to TR, which is the delta ky. And then aliasing can happen if the field of view is smaller than the subject in this dimension. Okay, so that covers field of view. Next, I want to cover image resolution or pixel spies. And as we've now getting used to, is that the finer features of the images are really defined by the edge of the K-space. Okay, or the other way to think about this is the further out in K-space where we require data, the finer the resolution that our image is going to have. And the other way of looking at that is we're measuring higher spatial frequencies, so more rapid spatial oscillations, which corresponds to and better spatial resolution. Okay, so it turns out there's going to be a similar inverse relationship between our sampling characteristics in K-space and our image. There's going to be this inverse relationship, but now the inverse kind of goes the opposite way. So what we're going to look at is how far we've gone in K-space. And remember, the intuition here is that the further we go in K-space, the higher spatial frequencies we're capturing, so the finer features we're capturing. And for example, the image resolution, which is, for example, delta x, is going to be the inverse of, and I'm going to use slightly different notation. I'm going to use this term width of kx to define the sampling width, so how far we go in K-space in the kx and ky directions. And so these relationships say the further we go out in K-space in kx and ky, the finer or smaller our spatial resolution, our image resolution becomes. So let's put this value to test in our pull sequence and see if we can calculate it out based on some parameters. So as we require our phase encoding line, then we want to know, what is this width that we're covering here in the kx dimension? Or that's going to be illustrated here in this height. What is the width in the kx dimension here? And we can write this in a couple of different ways. But again, we're looking at gradient areas. So it turns out this is going to be the entire, we'll look at the entire gradient area of the readout gradient. This is determines the total amount of distance we're traveling in K-space during this interval. And to know that, we have to know, the total duration. And here's the notation that I'll use. It's t read. The other way you can put that is you could say, well, if here this is the sample spacing, delta ts, it's that sample spacing times NFE, which is the number of frequency encoding points or number of frequency encoding samples. Then, with this information in hand, say the width that will travel is travel magnetic ratio times the readout gradient times this total readout duration, or the field of view, or not the field of view, we did that already, the resolution in x is going to be 1 over the total width in x which is just 1 over this gradient area. And interestingly, you can also rewrite this in terms of the field of view in x divided by the number of frequency encoding points. So this is actually defining our field of view divided up in NFE points, gives our spatial resolution. And this is, if you think about it, this is what we should expect. Okay, so for defining the resolution in our phase encoding dimension, we want to know actually our two extremes when we sample one edge of K-space, and when we sample the other edge of K-space, we need to know what is this distance, what is the width in KY. We're going to go to our two ends in the phase encoding sampling, and that's also going to correspond to this here. And we're talking about K-space, it's all about gradient area, so it turns out this is going to be proportional to this gradient area that I've annotated here. And so we can determine what that is by knowing the phase encoding gradient duration. Here's the notation that I will use for the minimum and maximum, so the GYP standing for GY peak of the phase encoding gradient amplitude. And so we'll determine this width in KY, and it's going to be, and I'm going to put an approximate symbol here because we usually add, because of some properties of discrete sampling, we usually add a half sample here to make this definition precise. So, but this is very close. It's going to be gamma bar times, and I'll do the time first, times twice this GY peak amplitude. So that's this total yellow gradient here, area here. This means that the field of view in the Y dimension is the inverse of this width. So just copying that here. I want to note that if we think about, we're going to do, say we're going to do NPE phase encoding steps. This means that GYP and again, approximate here, there's like a factor of a 1/2 or 1 or 1/2 that needs to come in here. For large several hundred phase encodes, this doesn't make much difference. But the GY peak is going to be the, or in fact, 2 times the GY peak is going to be the GY increment that we defined before. So when we change between phase encoding lines, we increment the gradient by some amount, and we repeat this NPE times, we should go between our minimum and our maximum gradient amplitude here. And you can go through and determine that the resolution in the phase encoding direction is also going to be the field of view in the phase encoding direction, but divided by the number of phase encoding points. Okay, so I'd just like to summarize and illustrate that here. And I'm going to annotate, and since we're looking at gradient areas, where we can find all of our key parameters here for the field of view and the resolution. So, so first, based on the sampling duration here, we can get the field of view, and X is 1 over the sample spacing in Kx, the resolution in X is going to correspond to this, and total width that we travel in the Kx dimension. The field of view in the Y dimension corresponds to this delta ky based on the gradient increment between TRs. And finally, the resolution in Y depends on this, again, the width that we're traveling in the ky dimension. That's sort of the maximum extent of our gradient variation that's going to occur. Okay, and you'll be able to calculate, now you have formulas to calculate all these things out based on receiver bandwidth, gradient amplitudes, gradient increments, gradient durations, both for field of view and for resolution. And so with that, hopefully want to make sure you can understand both the definition of these terms, field of view and resolution, and then understand how these are calculated based on either frequency encoding or more generally with using the k-space interpretation, and then this concept, and then how this affects aliasing. So what are our sampling requirements to prevent aliasing, and how is aliasing different in the frequency and phase encoding directions? Okay, thank you for watching.